we understand a little bit about power flow on a transmission line, it's about time for us to start thinking about playing some games, playing some impedance games to really get any impedance that we like on a transmission line. And you may be a little bit surprised. You're like, how on earth can you basically start with just a load and excite the transmission line and try to get variable impedances? Well, I gave you the equations before, but here we will see a little bit more explicitly the beauty of basically getting any impedance you like on a transmission line. Let me remind you that this all comes from the fact that as you start moving some distance away from the load, you start gaining that liberty of defining different impedances as a function of L. And as this equation might already imply to you, ZL is not just close, by ZL I mean this one here, is not just close to the load impedance. It can actually be vastly different. We'll see an example in just a minute that it can actually go from open to short and back to short and back to open, and it really varies quite dramatically. So let me give you some explicit examples here so you can get a real feel of how this thing works. So let's assume that I do have a transmission line that is actually shorted at the end. So here's a transmission line Z0 with literally a short at the load. This is something you can do in real life really easily. Just literally take two pieces of wire and just short them at one end. What we will find out is that even though ZL clearly, when L is equal to 0, is equal to 0 ohms, of course that's what the short is, as you start moving away, you will basically find out that this can change quite dramatically. So let's see that. So gamma L, let's start with finding the reflection coefficient for my load. So gamma L is equal to ZL minus Z0 over ZL plus Z0. And in fact, since my ZL here is equal to 0, this is nothing else but -1. So the first thing you should really remember is that when you have a short circuit, that comes with a reflection coefficient of -1, or if you want to express it differently, that will have a magnitude of 1 and a phase of 180 degrees. Now, VSWR, which is basically 1 plus magnitude of gamma L over 1 minus magnitude of gamma L, is going to be equal to infinity. That's basically the extreme case of the short circuit. Even though I'm not writing here explicitly, I do want to remind you that this means that P reflected is basically going to be equal to 100% of the P incident, since my magnitude of gamma L is equal to 1. And that should not really surprise you, because the short circuit consumes no power. So the power at the load, which is the incident minus the reflected, should actually be equal to 0. A short circuit doesn't really consume any power. Now, if I go and write down the expressions for V of Z, this will be equal to V0 plus e to the negative j beta z for the incident wave. Now, my gamma L is -1, so this will be negative e to the plus j beta z, which basically means that this will be equal to -2j if I do the exponential calculation, V0 plus sine of beta z. So we have this interesting voltage equation, and similarly you can get the current equation simply by dividing. Oh, by the way, let me actually write this thing as a function of L. So this will be equal to 2j V0 plus sine beta L. So I basically replace z with -L. And so I can basically find out now my current, which I can take my voltage and simply divide by the impedance. And this will give me well, let me correct that. I'm applying the equation I had before for the current, so I have to be a little bit more careful here. So I'm applying the equation I had before for the current, and if you do this math, it will be 2 V0 plus cosine beta L divided by Z0. So because in the current case, you will have exponential e to the -j beta z plus e to the j beta z. So now if you divide V by Z, V by I, you will basically get the input impedance as a function of L. So again, this is going to be the voltage divided by the current. And if you basically just look at that, it will be equal to JZ naught tangent beta L. So just by looking at this equation here, you should know that basically my Z input can practically be any number I want depending on what the number tangent beta L is. And so if I can show you this graphically, I'll go to my next slide, and you will see that when I have a short circuit, ZL is equal to 0, my impedance at any point in the line is exactly what I derived before. So Z naught tangent beta L. And I have graphed here my voltage magnitude as well as my current magnitude along this line. So let's look at these graphs a little bit more carefully here. With the blue line, you can see the transmission line. At the end of this transmission line, I have my short circuit. So at the Z equals 0, I have my load to be equal to 0. And clearly, that should mean that my voltage should have a 0 value, and it does. And it also repeats, as we know, every lambda by 2. So if I move lambda by 2 away from my short, I will indeed get another 0 voltage value. While if I just move lambda by 4 away, which is here, I will get now a maximum value. Now, exactly the same thing happens for the current, except things are reversed. So at the short location, I should have a maximum current, and indeed I do. The maximum current is 2 V naught plus divided by Z naught. I move lambda by 2 away, I find another location of a current maximum, but I move lambda by 4 away, and my current is actually 0, as it should be. So, in other words, just by moving quarter wavelength away, you go from having a short circuit to having an open circuit with a maximum voltage and a 0 current. So this idea of essentially changing impedances between short and open or open to short in a shorter transmission line is very, very powerful. And again, it only takes quarter of a wavelength to make that happen. Now, of course, when you were taking undergraduate courses and you were designing circuits, usually those circuits were at very, really low frequencies, which meant that lambda was actually a very large number. And of course, if you're designing a circuit at 1 megahertz, lambda is really large compared to the physical dimension of your circuit, so you will never see that effect. But when lambda starts becoming 1 centimeter, 1 millimeter, then very quickly, unless you're very careful, you can run into trouble.